square is a constant. Derivative of y square is 2 into y into derivative of y, which is a y1. So this is what we get. Quickly confirm. Yeah, we are doing differentiation again because straight away we're not able to apply the Leibniz rule. We're not able to apply the Leibniz rule. Yeah, it is the square of a function given there. Y1 square is there, y square is there. I'm not able to apply Leibniz rule. So to apply Leibniz rule, we're trying to see if we can differentiate one more time and get in just terms of y or y1 or y2 or y3 and so on, and not a y1 square, a y2 square and so on. For that, we're doing it. Okay, so once we finish this one, throughout he's cancelled out the factor 2y1, which is there in all the steps. When you cancel the common factor 2y1 on left hand side and right hand side, confirm whether you get this equation. Confirm whether we get this equation. Yes, we're cancelling the common factor there. Yeah. Okay, so once we cancel the common factor, all of you are confirming that this is what you got. Now let's see whether Leibniz theorem can be applied. Look at the left hand side, 1 minus x square into y2. Then I can apply Leibniz on xy1 also, because Leibniz is about product of two functions. I have a 1 minus x square, I have a y2. Yes, I can apply Leibniz on the first term. Come to the second term, I have an x, I have a y1. I can apply Leibniz on the second term. Right hand side is just a one function y, and its derivative straight away gives me an m square yn. Okay, if I differentiate n times, straight away my right hand side gives me our m square yn, because it's the nth derivative that we're trying to find using Leibniz theorem. Start with the first term, 1 minus x square into y2. Okay, 1 minus x square into y2. nc0, put up the values there. nc0, yeah, 1 into first function as it is, the nth derivative of y2, which is a yn plus 2, plus nc1. nc1, give me the answers. N, so I can see an n here. First derivative of 1 minus x square, which is a minus 2x, and reduce the nth derivative of y2. Earlier it was yn plus 2, so now it became a yn plus 1. So that's the second term. Move on to the third term, nc2. We finish with nc0, nc1. Now it's an nc2, n into n minus 1 by 2. So I can see an n into n minus 1 by 2. What about the derivative of 2x? Do we get a 2? Derivative of 2x. Do we have a 2? Will that 2 and this 2 get cancelled out? Derivative of 2x is a 2, that 2 and this n into n minus 1 by 2, 2 got cancelled out, and yn plus 1 is further reduced to yn. Now, will any more terms come? You started with 1 minus x square, you put its derivative minus 2x, you put its derivative minus 2. The next derivative would be? Next derivative would be 0. Yeah, so this first term is just giving us 3 terms. So these are the 3 terms that we'll get. Next, start with a minus xy1. Okay, how many terms do you think we'll get? xy1, function as it is, x as it is, x derivative 1 will come, and then after that it is 0. So xy1, we are expecting how many terms? Only 2 terms, okay? Because xy1, you will have function as it is coming and its derivative 1 coming. After that, it's not going to appear because derivatives would be a 0. But nc0 is a 1, so minus xy, minus xy1, minus x came as it is. Nth derivative of y1 is a yn plus 1. Okay, so nth derivative of yn is a yn plus 1. Next, derivative of minus x is a minus 1. nc1 is an n, and yn plus 1 is now reduced to yn. So we just have 2 terms from xy1 and 3 terms from 1 minus x square into y2. And right hand side, it is just an m square yn, which is the nth derivative of y. So till here, confirm whether it's right or mention or repeat if you haven't got it. Right, I don't see a repeat, so I'm assuming you've understood. Now, the second equation is just simplifying that equation. Now, yn plus 2, throughout you check, there's just one term, so that yn plus 2 term we kept as it is. Okay, there's just one term, which is yn plus 2. Next, yn plus 1, I can see one term here, take a common out. You can see within brackets, you're able to get, yeah, 2n here and a 1 there because you're taking x into yn plus 1 common out. Okay, so two terms came for your yn plus 1 term. Next, what about your yn term? Bring everything to the left hand side and then take a yn common out. So you can see a minus n square here, my plus n here, a minus n here, and a minus m square. So if I take a common out within brackets, do I get an n square plus m square into yn? Just take common out and quickly confirm whether this equation is right. A plus n and a minus n is getting cancelled out when you're taking common out for yn. Carefully check and confirm whether this equation is right, because we're almost done. We just got this equation and now we apply this equation. If the equation is correct, mention a correct. Yeah, till here it's right. Mention a correct there. Mention a right. For yn common out, why didn't we take the n out? Okay. There is my right hand side, there's no n. Look at the right hand side term. You have just an m square there. Right hand side term has an m square. It doesn't have an n, so we can't take common out because you're taking the right hand side term also to the left hand side and then taking a yn common out. So when I move the right hand side term, yeah, we're moving the right hand side m square yn to the left hand side and then we're taking it common out. Yeah. So m squared yn doesn't have an n there, so I'm not able to take an nyn common out. Okay, okay. Right. So all of you seem to have confirmed that this equation is right. Now, if it were the question was about just finding the nth derivative, we would have stopped here. But question was about finding the value of the nth derivative. Yeah. So this is about finding the value of the nth derivative. So that is why in this equation which you just got, wherever x is there, put a 0 and confirm to me whether this equation is right. Wherever x is there, put a 0 and then confirm to me whether this equation is right. Okay, yn plus 2 is a function of x. So that is why when I'm putting a 0 there, I'm not writing just a yn plus 2. I'm not putting just a yn plus 2. Yn plus 2 of 0. Because y is a function of x. So left hand side, you can see a yn plus 2 of 0. Second term is a 0 because x is a 0. What about the third term? Third term is a yn of 0. Okay, there's no x involved in the third term. Take it to the right hand side. You can see that it is an n square plus m square. And then within brackets again, you're writing a yn of 0. Okay, this is what you're writing. Confirm whether what we written is right. Mention a correct if you've reached till here. Wherever x is there, we put a 0. Do we get this equation? Okay. Why is it of 0? Because y is a function of x. In place of x, if you put a 0, the first term, okay, it has a value. 1 minus x square has a value because the moment you put x to be 0, the value of that expression is 1. But yn plus 2, you can't comment on it because y is a function of x. You can only say what is the value of yn plus 2 when x is 0. So that's why we are writing of 0. That means what we're trying, see, what a y of 0 means. Y of 0 means the value of y when x is equal to 0. Or what is an f of 0? F of 0 means the value of the function when x is a 0. So same case, yn plus 2, you can't have its value. You're not able to comment on its value as of now. You're only saying yn plus 2 of 0. That means put wherever x is there, whatever be that value, that is nothing but your yn plus 2 of 0. Got it? Or do you want me to try again? Because this means that the value of the function yn plus 2 when x is 0. That's what we are saying in our minds when we read this expression. Because look at f of 0. What is an f of 0? The value of the function when x is 0. That's how you read this, right? How do you read an f of 0? It's not an f into 0, right? F of 0. That means the value of the function f at x equal to 0. So same is the case. Y of 0 means the value of y at x equal to 0. Yeah. Yn plus 2 of 0 means the value of yn plus 2 at x equal to 0. Yeah, instead of putting comma x equal to 0 at x equal to 0, we just putting in brackets and trying to say that this is nothing but the value of the function at x equal to 0. Okay, get used to writing it this way because all the textbooks that we use, this is how they write. Okay, what we mean to say is at x equal to 0 only. Clear? Or repeat? Okay. Can you see the last step? Last step, I think, yeah, difficult to see, but I will read it out. Okay, so now we got the most important equation because from this equation, yeah, we can get values. Okay, so this is about the nth derivative equation. This is about the values equation. Now we can comment on the values. Start with this one. Okay, so to use this equation first, yeah, let's find the initial values of y of 0, a y1 of 0, a y2 of 0, and then we start applying in this equation, right? Because we want to comment on the nth derivative of 0. We want to comment on the nth derivative of at x equal to 0. So let's just comment on the first things that we know. Start with this one. Whenever x is 0, what is y? When x is equal to 0, what is y? Look at this equation, first one. When x is 0, what is y? Is it an e power 0, which is 1? Yeah, so we are writing y when x is equal to 0 is 1. Clear? Y of 0, is it 1? Any repeat for y of 0? Because we examined y, we went to y and wherever x is there, we put a 0 and then we commented that y of 0 is 1. Next, come to this equation, second equation. Wherever x is there, put a 0 and give me the answer for y1 of 0. Wherever x is there, put a 0 and comment on the y1 of 0. So is it an m? So this equation is also confirmed by you. You're saying that equation is also right. Y of 0 is 1, y1 of 0 is m. Any repeat? We're going to each of those equations and putting an x equal to 0 there. Okay, I don't see a repeat, so I'm assuming you've understood. Right. Next one, we finished with y, we finished with y1. Is this the equation which involves y2? Is this the equation which involves y2? Yes? Okay. So if this is the equation which involves y2, now wherever x is there, put a 0. Wherever x is there, put a 0. So if x is there 0, then first term, will it become a y2 of 0? Would it become like this? Would it become just a y2 of 0? Left hand side, check carefully. When x is 0, is it a y2 of 0? Right. What about right hand side? Right hand side, I have an m square, but whenever x is there 0, y I need to mention as, what do I need to mention it as? I need to mention it as a y of 0. But what is y of 0 by what you've already found? It is a 1. So can we conclude that y2 of 0 is nothing but your m square? Mentioner, repeat if you haven't got it. We found y of 0, we found y1 of 0. Next, we want to find y2 of 0. So we went to an equation involving y2. So you said this is the equation which involves y2. In this equation, wherever x is there, put a 0. Wherever x is there, put a 0. What is left of the left-hand side term? Left-hand side, whenever x is there, if you put a 0, is only a y2 of 0 left on the left-hand side. Syed, only a y2 of 0 left on the left-hand side. Move to the right-hand side. Right-hand side, wherever x is there, if you put a 0, you get an m square into y of 0. M square into y of 0. Because you don't know the value of y. Yeah, so m square y of 0, but y of 0 you had already evaluated and you said it's a 1. So in place of that, if you put a 1, you get your y2 of 0 to be m square. So we got the initial three values. Now that I know y2, can I go back to this equation and find y3? Confirm? I have y of 0, I have y1 of 0, we have y2 of 0. Can we go to this equation and find y3? What will I put in place of n? If I want to find y3 of 0, in place of n, I need to put 1. So will it become a 1 plus m square into y1 of 0? And what is that y1 of 0? 1, right? Yeah, so if y2 is there, next we want to find y3. This is serving as a recurrence formula. That means I can use this formula again and again. I know y3, I know y2, I can find y3. I know y3, I can find y4. With y4, I can find y5. So this is a kind of recurrence formula. Since we already know y2 of 0 is m square, y3 of 0 will be, in place of n, put a 1, and then it's a 1 plus m square, and a y1 of 0 is an m, so you will get a 1 plus m square into m. Do you get that? Yeah, almost like a pattern recognition. Yeah. Okay. What I'm trying to say is we have a formula. First three we found by going directly to those equations, because we have an equation for y, we have an equation for y1, we have an equation for y2. There we went and substituted and got the three values. So this much you've already confirmed with me that y of 0 is right, y1 of 0 is right, y2 of 0 is right. I want to find y3 of 0, but we don't have an equation involving y3, right? We just found the second derivative and applied Leibniz to get the nth derivative. So we don't have a particular place where we can go and get the y3 of 0. So we are using this formula which we got, because this is a formula of nth derivative which should work for all possible n's. So y3 I should get it from there, y4 I should get it from there, or y100 I can get from there. So I'm going back to this formula and trying to find y3 of 0. Y3 means, look at this one. What is the value of n that I will put to get y3? Neon, if to get y3, what will I put in place of n? A yn plus 2 of 0 is there. So I will put in place of n of 1. Yes or no, Neon? Yeah, because we want y3. So in place of n, put a 1. So what will happen to the right-hand side expression? In place of n, when I put 1 in within brackets, do I get a 1 plus m square? Yes, we put a 1 plus m square, and then y, in place of n, you're putting a 1. So this yn of 0 now becomes a y1 of 0, but you already have a value for y1 of 0, which is nothing but m. So y3, y3 of 0 gives us a 1 plus m square with an m outside the brackets. Yes or no, Neon? 1 plus m square within brackets with an m outside. Yeah. Syed has a doubt. Others, please clarify. Instead of x equal to 0, if we put x equal to 1, do we put it? What is given? Why don't you finish solving, Syed? Syed, what is given? Let's finish first. Okay, y1 of 0, how is it an m? Okay, so this is where we went. This is the equation which involves y1. Wherever x is there, put a 0, e power 0, 1, m upon square root of 1, which is a 1. So is y1 of 0 m? Confirm, Rishikesh? Wherever x is there, put a 0, and then can we say that y1 of 0 is an m, because e power 0 is 1 and a square root of 1 minus x square is 1. I'm getting it from this equation. Yeah, no, not from this one. This one you can't comment. You can only start with a y2 of 0 from here. No, yeah, a y2 of 0 we could have got from here. No. Yeah, we can only get from y3. We can't even get from y2. Yeah. You can't get from y2. You can only get from y3 from this equation. Yes, that's why we had to find y of 0, y1 of 0, y2 of 0 separately and then substitute. Okay, so I'm moving on, assuming you've understood. So we'll go to the next part of the question. How did we get y2? Okay, we went to this equation. This is the equation where we put wherever x is there, we put a 0, and then we said y2 of 0 is only left on the left-hand side. If x is a 0, only a y2 of 0 is left on the left-hand side. And right-hand side, y of 0 will come, because you're putting an x equal to 0 here. Syed, please don't confuse us, Syed. Let's handle an x equal to 0. Later on, we'll go for x equal to 1. Where is it? Which one are you talking about? On the right hand side of the final rearranged equation. This one. Is it this, Syed? Above. Okay, this one. Yeah. What is it you want? Instead of x equal to 0, if we put x equal to 1. Huh. Yeah. Yes. What is an f of 1? Syed, it's the value of the function at x equal to 1. F of 0 is the value of the function at x equal to 0. Okay. Y of 0 is the value of y at 0. Y of 1 is value of y at 1. Y of 1,000 is the value of y at 1,000. Okay, the others please address his doubts. I am moving ahead. Yeah. One of you quickly answer. Who's asked me about this one to check what is y2 of 0? Did you get it? Please confirm. Or somebody, I repeated this. Please confirm if you got it. A y2 of 0, we wanted to show that it is an m square. So wherever x is there, we put a 0 and we got a y2 of 0 equal to m square into y of 0. But y of 0 is 1. So that is why, yeah, y2 of 0 is an m square. Confirmed? Or is it a repeat? Yeah, one of you quickly confirm. Rishikesh, confirm. Is the y2 of 0 clear? Right, okay. Otherwise, we'll come back to it. Yeah, so now we have this equation, which is the recurrence formula that we got. We called it the recurrence formula. So this particular formula start with y3 of 0. So y3 of 0 means you said in place of n, a 1 will come. So 1 square plus m square into m. So this is what you already confirmed with me about a y3 of 0. Next, go for a y4 of 0. y4 means in place of n, what do you put? Look at this and tell me in place of n, what will you put if you want your y4 of 0? 2. Yeah, so 2 square plus m square into y2 of 0. Okay, because yn plus 2, it's a yn. So y3, it's a y1. y4, it's a y2, y5, it's a y3, and y6, it's a y4 which will appear. So then when you substitute, you will see that these are the terms which will appear. Till here, one by one, you check and confirm and let me know. Then we'll proceed. Till here, I want you to confirm whether all these four equations are right, looking at this recurrence formula, and then we continue. Hurry up. Take a 2 minutes time to complete that job. If it's correct, mention a correct in the chat box. Yes, I want all of you to confirm, not just 2 or 3 of you. Yeah, whoever is solving with me will confirm. Right. Okay. Yeah. So what we'll now do is we'll try to generalize. We got y2, y1, y2, y3, y4, y5, y6. Can we now comment on yn? Because interest to us is yn. What is the value of yn at x equal to 0? So looking at this, we're seeing a pattern there. With that pattern, we want to find what is yn of 0 because that is of interest to us. So he's trying to generalize, quickly check whether it's right. When n is even, so basically you are looking at these cases, y4, yeah, y6, okay, these cases you're looking and then you're commenting on yn when n is even. And you're looking at a y3, y5 and commenting on when n is odd. So carefully check an m square, 2 square plus m square, 4 square plus m square, and so on is coming. So if I had gone for one more term, what would have come within brackets? Can you comment? If I had gone for one more term, what would I have got? What would I get in the as the next term? Had I gone for y8, what would have come within brackets? For a y6, you can see a 2 square, 4 square. Yeah, 6 square would have come. So for y6, it is 4. Yn, is it n minus 2? Quickly confirm. For a y6, it is 4 square. For a yn, is it an n minus 2 whole square? Confirm or repeat? Yeah, so you're confirming. So that would be the term. That would be the last term. Right. Okay, start with odd terms. Odd is m into 1 square plus m square when it's a 3. Okay. M into 1 square plus m square into 3 square plus m square when it is 5. So for 5, it is 3 square. For n, it is n minus 2 whole square. This term is also right. For a 5, it is 3 square, the last term. For an n, it is n minus 2 square. Only difference is these terms are different from these terms. Okay, but we are able to see that there's a pattern. So when n is even, this is the answer. When n is odd, this is the answer. Any repeats? Generalizing, because our interest question was about this. What is the value of nth derivative at x equal to 0? That's the question. What is the value of nth derivative at x equal to 0? Yeah. Okay. So from y3, y4, y5, y6, we are trying to comment on yn. Y3, Y4, Y6, we are trying to comment on Yn. So start with the even terms. First, let's begin with the even terms. We considered a V4, we considered a V6. So V6 has a 4 square coming within brackets. So I asked you what will come for Yn. You said an n minus 2 whole square will come. But for a 6, it's a 4 square. For a 4, it is a 2 square. So for an n, it is an n minus 2 whole square plus m square, which will be the last term. So pattern is this: m square into 2 square plus m square into 4 square plus m square dot dot dot. Last term would be an n minus 2 whole square plus m square. Yeah. Okay, so that's about the even terms. Move on to the odd terms. Odd terms for a y3, it's a 1 square. For a y5, it is a it is a 3 square. So for a yn, it is an n minus 2 whole square plus m square, and pattern is this one. So this is how we get for n is odd and n is even. Okay, I'll come back to your doubts. First one is, yeah, because it's a different pattern for odd and it's a different pattern that's coming for even. That is why we are forced to write it like that. It's not the same sequence that you see there. Same type of factors are not appearing for both the cases. An m is coming ahead for the odd terms and an m square is coming ahead for the even terms. Did you get it, Eon? Yeah. Oh my God, you want to get factorials also. Why will factorials come, Sayed? These are terms. Yeah, these are not successive terms. How do we know whether what will follow a 6 would be a 5 or what would follow a 6 would be a 7? See, factorials come when you have integers successively appearing. Then only we'll bring in factorials. These can't have factorials. These, okay, try to evaluate this. Put an m equal to put an m equal to 0 here and tell me whether the factors will have successive numbers coming, Syed. Put an m equal to 0 and tell me whether you have successive numbers coming. No, no. Yeah, only when it is unavoidable, bring in your factorials. Otherwise, just try to avoid factorials because why do you want to complicate what is already complicated? Got it, Syed? Yes, Arpan. How will you use modular arithmetic there? Modulo, what will you bring? See, why do we use a modulo function? Arpan, yeah. Why do we use a modulo function? So that we don't have those large numbers and we keep try to identify the smallest negative number. Okay, so to limit our wide answers, that's when we want to use a modular function. Yeah, I I really don't know how a modulo function would help to this one. You only have to figure out and tell us. Yeah, I can't see how it will help us because see, modulo is basically about when I say 5 mod 3, what is it I'm doing? I am trying to get the remainder left when I divide 5 by a 3. Okay, to simplify whatever we have. Yeah, so supposing a 3000 mod 2, mod 7 is there. So what is the remainder left when 3000 is divided by 7? That's the question. Yeah. So when we want simplified answers, we get, but how do we get simplified answers? These already are m power n mod 2 for power. No, beyond my scope, Arpan. I'm not able to answer those. Yeah, no, I don't. Some other day we'll have a discussion because you have to explain it to us. I don't get it. Yeah, I find it tough to understand. Anyways, yeah. Sorry, Arpan, I'm not able to clarify your doubt, nor am I able to confirm that it is right because I don't have so much understanding in that. Yeah. Okay. Right. Okay. Any more queries on this slide? Am I moving ahead? Hurry up, hurry up. We just have a few more minutes. Have we done just one question today? Oh, what a shame. You're supposed to do 5 questions. No, we're supposed to complete 5 questions. Okay. Yeah, I'm not able to extend it further because we have a meeting at 2 and I haven't made any preparation, yeah, for that. So I need to do something for that also. So I need to leave exactly at 1. Yeah. Yes. So this looks like a simple one. Shall we just look at the question, quickly go through the steps, and you will solve it later on by yourself? Okay. Let's quickly see what the question is about. You have your first function to be x, second function to be a 2x plus 3 whole cube. Okay. Go back to your nth derivative formula for a 2x plus 3 whole cube. Which is the formula? Is it an ax plus b raised to the power k that you have already done? In the nth derivative, ax plus b raised to the power k is what we have done. Right. Okay, let's begin this. So we are applying the nth derivative. We are applying the Leibniz rule. So he's just stating the Leibniz rule, and then he's saying nc0 is 1, nc1 is n, and then he puts nc2 is an n into n minus 1 by 2. Then he puts an nc3 term, which is an n into n minus 1 into n minus 2 by 3 factorial. Yeah. And then the NCN term. Okay. NC3, we finished with an NC4. Okay. And then other terms, he's saying they become 0. Okay. So we'll quickly check whether each of those terms, he's saying nth derivative of first function, second function as it is. Then n minus 1th derivative of the first function and first derivative of the second function. N minus 2th derivative of the first function and then the second derivative of the second function. N minus third derivative, this should become an n minus 3. Okay, so typo. Yeah. Check again. Is it n minus 3 that would come? Because this is a dn minus 2. So this is a dn minus 3 of ex. And then this is not a plus. This is a multiplication which would have which should appear here. And then it's a d cube of 2x plus 3 whole cube. Okay. 2x plus 3 whole cube. Can it have the fourth derivative? Give me an answer. Yes or no? Okay. Its fourth derivative is going to be 0. So if I were in your place, I would if I was there in your place, I would skip all this and straight away come from the formula to this term itself. Okay, so no marks for writing this many steps there. Yeah, you have to state the Leibniz rule. Definitely marks will be there for stating the Leibniz rule. And then let's straight away apply. MC0 is 1. First function is e power x into second function 2 power x plus 3 whole cube. 3 whole cube as it is. That means he differentiated e power x once and he got an e power x only. Second one, nc1 is an n. Derivative of e power x is again an e power x, but derivative of 2x plus 3 whole cube is 3 into 2x plus 3 whole square into 2. Confirm till here. Check whether these two steps are right. First two steps are right. If you confirm, I'll move on to the third step. Hurry up, hurry up. Don't copy the formula. Don't copy those steps. Unnecessary things you remove. Straight away come to this one. Okay. Yeah, so you're confirming that these two steps are right. Let's move on to the third step. We finished with NC0, we finished with NC1, so NC2. So that's why you're writing an n into n minus 1 by 2 factorial. And derivative of e power x is yet another e power x. And then derivative of 2x plus 3 whole square brings a 2 ahead. So that's a 6 into 2x plus 3 into 2. Okay, so is there 2 missing there? Already we have a 6. Now another 2 has come. So 6 into 2 into 2. Correct. Yeah. So into 2x plus 3. That's the next term. Then we have an NC3. So n into n minus 1 into n minus 2 factorial by 3 factorial. Derivative of e power x is again an e power x. And then look at these coefficients. 6 into 4, 24 is already there. And then 2x plus 3 derivative just comes with a 2. So this is our last step. This is our last step. Confirm whether last term is right. Confirm, because you confirm the first two terms. I want you to confirm the last two terms. If they are right, we proceed. Otherwise, mention a repeat. Yes? Okay. If that is repeat, is the simplified version this? Solve and tell me whether this equation is also right. Okay. We are just simplifying, taking common out, simplification, all that we should be able to do. And finally, you confirm whether this equation is right. I'm not teaching people how to take a common out, cancel terms, do all that. And one of you confirm that this last equation is right. I will move ahead. Hurry up, hurry up. 2 minutes you take and try to simplify. 2x plus 3 power 3 term, 2x plus 3 power 2 term, 2x plus 3 power 1 term, and then the term which does not involve 2x plus 3. Pallavi is already confirming that it is right. You checked all the. Okay. This is a solved example in NP Bali Vibhu says. Yeah, those of you have your NP Bali already. Yeah, soft copies with you. You can check. This is a solved example from NP Bali. Yes, if you confirm, we move ahead, and then I'll get a little greedy and try to do one more question. That's why I want you to confirm at the earliest. Okay, so don't write these steps. These steps we will avoid. Okay, there's no marks for writing d power n of e power x and all that. This we will totally avoid. Yeah, straight away we write the formula of Leibniz and then we come and apply them directly to both our functions. So in between steps we will skip. Yes, Manjari. Okay. Can we choose any u and v? Yes, it's up to us. Any u and v doesn't really matter here. Both have to be exhausted. Both their derivatives have to be exhausted. Yeah, the moment one of them gets a derivative 0, it's very convenient. Those terms we don't have to, yeah, we don't have to work out on those steps. So always our focus is on which one is going to get exhausted. Here, e power x is there, we know it's going forever. but 2x plus 3 power 3, you said fourth derivative itself is 0. So we know we only have to figure out the third derivative. Shall I move ahead? Mention doing it if you're doing it. We just want to see what is there next, whether anything that can be done in 2 minutes. I want to check. Mention doing it if you're doing it. I don't see you doing it, so I'm assuming you've finished. Have you finished? Okay, Bhavya, go ahead, finish it. Yeah, Leibniz is not easy because it's confusing. So many terms, you have to be constant of those coefficients also. Sometimes we'll just forget those coefficients, MC0, MC1, and so on. We'll just handle function derivative, this derivative, that derivative. Yeah, it is not easy. It is difficult. Where this one, Arpan? Is it this? Are you talking about this one, this term? Okay. So we first time we got, yeah, 2x plus 3 whole cube is a 3 into 2x plus 2 whole square into derivative of 2x plus 3, which is a 2. So first we got a coefficient of 6. Then we will again differentiate and we will get a 6 into 2 into coefficient of 2x, derivative of 2x plus 3, another 2. So 6 into 4, 24 is already there with us. Next, 2x plus 3 derivative will just give us a 2. So 24 into 2 is correct. 24 into 2 will be there because the 2x plus 3 derivative is also there. Twenty-four without differentiating, and after differentiating yet another 2. Check, Karpan, confirm. Yeah, 24 into 2 is there. Right, okay, so I just want to have a glance at what is next and then we, yeah. Okay, looks like a simple one. Shall we just finish it off quickly? Okay, okay. Let's do something. We spend one more class on Leibniz. Okay. Yeah, we'll spend one more class on Leibniz, but I will share these questions with you. Question number 8 is there already. Question number 9, some other question is there, log of this one. Okay, no, this I need to discuss. I can't share also. Yeah. Right. Okay. So one more class Monday we'll spend on Leibniz because I want to do a few more questions. Okay. Bye all of you. Bye. I'll stop sharing.